before I start modeling, I want to say one more thing that I forgot last hour. The projects will be conducted within groups of 2 or 3 within your own section, those small sections, all right? You have to be, because the practice on solvers are within your own section, so your project members will be together. And it is in the slide, in the syllabus, but you may not read it. You're supposed to come up with your project partners and send it to Zehra by 12 Thursday. We forgot to say which Thursday. It is next Thursday, because it has to be after the first practice session, all right? So next week, by Thursday, you're supposed to come up with your project groups. You have to form your project groups, all right? This Thursday is next Thursday. And all the emails are already here, the TAs and tutors, all right? You can always email us or them regarding the questions of the course. And you can get emails from any of us at any point. Any questions before I go on or I start real modeling? Any questions on the rules of the game and Piazza and practice hours? All clear? Okay. Then, let's start modeling. Decision-making problem. We will always be dealing with decision-making problems, right? So, what are the alternatives? Under what restrictions do you supposed to make the decision? So, what is your environment setting? And finally, what is your performance measure, right? Based on what are you going to optimize your decision? As decision-making problem. Now, we will start doing modeling examples together. What is a modeling example? I'll try to give you half a page of a problem description, and then we will end up with the actual mathematical model of it, all right? Let's start. We will have many of these kinds of examples. Milk projection, all right? Now we have a company that produces low-fat and regular milk, okay? And there are 2 machines in our company right now. And these are the times of those machines. You'll require both of those machines to work for the output, okay? So for low-fat milk, for example, for pasteurization, it requires 3 minutes per liter. And for homogenization, it requires 1 minute per liter, all right? Regular milk, 2 of each. Okay, looks like a very easy problem, right? 2 types of production, 2 types of products, low fat and regular, and 2 types of machines, pasteurization and homogenization, okay? So, what is the problem then? Let's see. Well, of course, keep telling you, the environment is giving us restrictions. Machine 1 can only be used for 12 hours, and machine 2 can only be used for 6 hours. Okay? Now, I have to make the decisions. Remember, each type of product uses different amounts of minutes from those machines. So I have to make my decisions based on these availability. What else? What is my performance measure? Of course, they do sell with different prices, right? The sales price of low-fat milk is 2.5, and regular milk is 1.5, okay? If I want to maximize my sales revenue, then I come up with a performance measure, and my environment is each type of product requires different amounts of minutes in each machine, and each machine can be used only certain hours of a day or a week. Then the problem is the red line there. How much low-fat and regular milk should be produced in a day to maximize my total revenue? Okay? How much of each should I produce? Now remember, given a decision-making problem, I have to know my performance measure. It's there, it says maximize our total revenue. I have to know my environment, and I have to come up with my decision variables. Decision variables are the things that I can change. I'm trying to find out, right? So in this problem, my decision variables are what? What are the decision variables? Come on. Say something. How many decision variables do I have? How many? Very good. Who said 2? Thank you very much. What are the variables? Can you say that too?
Money and time.
Nope. Money is when I sell that many, I'll get that. And time is I'm using those machines. I cannot change it. Yeah? 2 is a good number though, yeah? Amount of each time that I decide to produce. Regular milk, low-fat milk. How much of each? Those are my decision variables. Depending on their values, I will use different amounts of time from my machines, and I will gain different revenue. But those are the functions I'm supposed to write to represent the real life in my model, right? Let's see what I have in here. So what are the unknowns that should be determined by the decision maker? Those are actually my decision variables, x1 and x2. I represent it by x1, amount of liters of low-fat milk produced in a day, and x2 will represent regular milk. Low-fat milk, regular milk. Those are my decisions. Okay. These are called decision variables. Terminology that you should be learning. Decision variable. Finding the correct decision variable is the most crucial step in mathematical modeling. For certain problems, it's really easy. It's out there. For example, this one. For certain problems, it's not that easy, but I will walk you through a lot of examples so that we will come up with correct ones. All right, technical things, the environment, all right? What are the technical factors which are not under control? Like how many minutes irregular fat milk requires in the pasteurization machine? I cannot control that. It's given to me by my environment, all right? That's the rules I'm supposed to play with. So let's come up with those. What are them? Those are the technical things. So available machine hours. I cannot change the fact that machine 1 is available for 12 hours. So that's a setting for me. I have to live with it. Required machine hours for each product, like those 2, for a regular milk, it required 2 minutes of each machine. I cannot change that, yeah? And revenue, the sales price. Well, for certain problem, yeah, if come up with the price was an issue, yes, I can change it. But this time, no. I know the sales price, 2.5 and 1.5. So those are given to me. That's my environment. And I'm supposed to play within that environment and come up with the best option, yeah? What are they called? The things I keep telling you guys about my environment is actually the parameters or uncontrollable variables. Yes, they are again variables, but I cannot control them. So from my point of view, they are uncontrollable variables, right? Determining what is a variable and what is a parameter is very crucial, right? And you guys should be very, very good at it. What are the things that you can change are your decision variables, and the things that are set for you are your parameters, all right? Okay, physical limitations. Total production time on each machine. That's the thing I'm supposed to obey, right? I cannot make the machines work more than the required time or than the allowable time. So I have to write mathematical representations for those machine hours. And of course, I cannot produce negative amounts. And these will be called constraints in our mathematical model. So terminology, decision variable, the things I can change, in this example, regular fat and low fat milk that I'm producing. Parameters, things that I cannot change. And constraints, my physical limitations. And my performance measure will be my objective function. And in this case, total revenue was actually my performance measure, right? Like one would say produce 2 of each, the other one says produce 3 of each. Which one is better? I'll check the revenue, and based on the revenue, I'll choose which alternative is better, right? So that is my performance measure. And it will be called objective function. So, decision variable, things that I can change. Parameter, that's the environment's giving to me. Constraints, physical limitations. And objective function, my performance measure. So 4 terminology for the things for each mathematical model. Now we're going to model this one. So for this milk production, this is the syntax. You may remember this from 1022. We write our objective function, our performance measure on top. So in this problem, we're maximizing total revenue. Okay? Subject to, this is the format, all right? Machine 1 can work at most 12 hours. Machine 2 can work at most 6 hours. And I cannot produce negative amounts, right? You have to tell, because it's just mathematics, at the end, those are just numbers. We have to tell the model that those numbers cannot be negative. Otherwise, it's not going to make sense for my original decision problem, right? So these are my physical limitations. Let's see how it's going to look like then. Total revenue, the function. I was earning 2.5 for each liter of low-fat milk and 1.5 for each liter of regular milk. So their sum gives me my total revenue. Yeah? So this is my objective function. It's a function I use to represent my revenue. That's my performance measure, right? I'm going to maximize that sum then, right? So production time on machine 1. For each unit, let's see the numbers. Here it is. For machine 1, for each regular fat, I use 3 hours, and for each low fat, I use 3 hours. For each regular fat, I use 2 hours of machine 1, all right? And for machine 2, it's 1 for low fat, 2 for regular fat, right? I'm going to put these numbers into my physical limitation constraint. Now, let me go there. I was here, so total production time on machine 1. Remember, it was saying for each low-fat milk, I was using 3 hours, and for each regular milk, I was using 2 hours. So their sum should not be more than 12 hours. It was minutes, by the way, sorry. This 3 and 2 was minutes, all right? And the availability I know is in terms of hours. So this is the first representation of the physical limitation. Their sum shouldn't be more than 12 times 60, okay? Because machine 1 is only available 12 hours. If you write it for machine 2, this time low-fat milk requires 1 minute, and regular fat milk requires 2 minutes. And if you add that up, you're going to get this. X1 plus 2x2 should be less than or equal to 6 hours times 6 minutes, which is 360. All right? Production amounts should be non-negative, which will say that x1 plus x1 is non-negative, x2 is non-negative. So this is the mathematical model of the milk production. Any questions? It's that easy, yeah? All right. Now let me put the names. So objective function and constraints. Okay? Now I'm going to use this example to give you more and more terminology. This is an example of a linear programming model. Linear programming. Why linear? Because all the functions I had to come up with was linear. It was sum, sum, sum. I didn't need to multiply variables, no quadratic terms, no squares, triples. So it's a linear function, all right? First of all, let me go on these first. What was a feasible set? Any solution of those x1 and x2. So x1, 3, x2, 5. x1, 1,000, x3, 10,000, right? These are all different options. I'm in dimension 2, and each vector in dimension 2 can be a feasible solution depending on if they satisfy my constraints or not, yeah? So anything that satisfies 2 to 5, remember, number 1 was my objective function, my revenue function, and 2 and 3 was my machine limitations, and 4 and 5 was my non-negativity. So I was supposed to be in the first quadrant, and I have a certain constraints regarding their sums with their multiplications, right? So anything that satisfies 2 to 5 is called a feasible solution, right? And a union of all those feasible solutions is called the feasible set. You have to be very good in these terminology because these are really basics. Now, my performance measure is total revenue, all right? So among the ones in my feasible set, I want to choose the one which maximizes my total revenue, yeah? So that is gonna be called the optimal solution. And the value is the optimal value. You should know these from previous year. That's why I'm going it a little bit fast, but be careful. Feasible solution, 1 point that satisfies all the constraint. Feasible set, union of all such points. Optimal solution is the one that gives you the best objective function value based on your performance measure, right? And that's it. 3 definitions: feasible solution, feasible set, optimal solution. I told you this was an example of a linear program, but so it's just, but then let's generalize it, okay? We developed a linear program for milk production. Okay, regular fat, low fat, whatever. Now, let's look at the general form then. Normally, a linear program looks like this. On top, we have our objective function. We're either minimizing or maximizing, depending on our performance measure. We're doing that over C1x1 plus C2x, because it's linear. I have to have linear functions there, all right? So if if I'm in Rn, if my variables were from x1 to xn, okay? Then I'm either minimizing or maximizing a linear function of my variables. That's my objective function. Subject to my constraints. Yeah, let's look at it here. So I have it, C1 to Cn are my parameters. In the previous case, it was 2.5 and 1.5. In general, they are C1, C2, C3, it goes up to Cn, depending on my dimension. And remember, I had constraints. I had machine 1 and machine 2, first of all. Well, here it looked, well, normally my constraints look like this. This was the machine hours each thingy was requiring in those machines, the pasteurization and homogenization, right? There's some, so I have some parameters multiplied with the variables, less than or equal to, greater than or equal to my right-hand side, little b. Because, again, I need linear forms. And again, our x1 to xn are my decision variables. I'm okay in the sign restriction. It could be less than, greater than, equal to, but I need a linear function there. Those are my constraints. So this is how it looks like then. I'm minimizing or maximizing summation of the C's. Subject to, I have it less than or equal to constraints, greater than or equal to constraints, and equality constraints, and my sign restrictions. This is general. In our previous case, each variable was representing the amount I'm producing, so all my variables were non-negative, but depending on the application, it might be such that I may be defining a variable for something that should be negative. Then I can just tell my model that, you know what, those variables should be negative. Then when I'm solving it, I'll always come up with negative numbers for those axes. Again, depending on the application. But this is a general form of a linear program. Okay? Any questions? So x's are my decision variables. I'm in dimension n. In here, I have n decision variables. I have less than or equal to, greater than or equal to, or equality constraints. They're all fine. And my variables are less than or equal to, greater than or equal to, or unrestricted in sign. URS means unrestricted in sign, especially for data fitting and statistics examples. Those numbers can also be negative. And those C's, A's, and B's are my parameters, remember? In the milk production thingy, C's were 1.5 and 2.5. A's were the minutes in the machine, so 3, 1, 2, 2. And right-hand side B was 12 hours and 6 hours. Those are the parameters given to me. Okay. More generalization. So when I say NLP, I keep saying it has to be a linear program. Now, normally, there are actually a couple of assumptions underneath that. What are they? Proportionality and additivity. Let's read this together first. The contribution of each decision variable to the objective function or to each constraint is proportional to that value, proportional to its value. The contribution from decision variables are independent from one another, and their total should be the sum of the individual contributions. Well, what this fancy statement is trying to say is you have to have a linear function there, right? When my function improves by the proportional to the value of it, and the x1 and x2's contributions are independent to each other, both in my objective function and in my constraint. It is in the milk production case. For 10, it's 1.5 times 10. For 20, it's 1.5 times 20 in my revenue, right? So it's proportional to the value of it. And this being 10 has nothing to do with the proportion of it for the other one being 20, right? Yes, they're sharing the same resource, but their proportionality to the function is independent of each other. Yeah? Once I have linear functions, those two are proportionality and additivity are immediately satisfied. Divisibility. This is decision variables can get fractional values. It's liters. I could have say, okay, I produce 2.5 liters of regular fat milk and 10.5 of low fat milk. It's fine. That was allowed in the previous case. That is called divisibility. So we have proportionality and additivity, divisibility, and finally we have certainty. I know what am I going to get if I sell my low fat and regular, the 2.5s, 1.5s, all right? Those parameters give us the case. All input parameters are known with certainty. In this case, we have a linear program. Okay. Any questions in the basics? I'm moving a little bit further. I'm changing this milk thingy just a little bit. In the previous version, we were allowed to sell it in terms of liters. And all my parameters were in terms of per liter, the revenue and minutes. Now it says, you know what? You can't sell it in liters. You're going to sell it in cartons. So the numbers are the same, but it's per carton, no longer per liter. Okay? First of all, this is no longer an LP because divisibility is gone. You cannot sell 1.3 cartons of regular fat milk. It's not defined, yeah? So it's not an LP anymore, it's something else. But shall we formulate it? Yes, of course. But this time, we will just make a slight change in the definition of the variables. In the previous case, it was defined as the liters produced. Now I'm going to define it as cartons produced. All right? That's how I define. But be careful. In the previous case, I was writing x1 and x2 non-negative. Any number was fine. This time, I have to tell the model that those things should be integers. 1, 2, 3, 5, whatever. Right? Well, we could do that. And this is how it's scanned then. The numbers are the same, so the objective function looks the same. Constraints, 2, 3, 4, 5 looks the same, but I'm adding 2 more. Now we call these, also the previous one, without these two, y1 non-negative, y2 non-negative, we call them domain constraints. Remember, I'm telling you, so everything should be from the first quadrant, right? I'm in dimension R2, so anything that everybody is non-negative, first quadrant, is okay with me. So my domain is first quadrant, the ones that satisfies my first 2 constraints. Okay? It's again domain, but this time I'm again in the first quadrant, but I'm in the lattice points. Integer points only. Okay? This is no longer a linear program because assumption 2 is gone, divisibility is gone, but this is something else. We call it integer programs. This is an example for an integer programming model. It's fine. We're going to learn how to model these in this course, but we're not going to learn how to solve them. How to solve integer programming models is 303. Okay? But next week, we will be dealing with many variations on this integer domain, but we're not going to learn how to solve them, right? We're going to learn how to solve linear programs with this course. Okay. Any questions? Clear? All right. The last example of today. By the way, we will be dealing with different examples. So I suggest, I guess, like Thursday's lectures should also be in Piazza. You can take a look at them before coming to class. Blending. I'm trying to make my life harder a little bit at each example. So in the previous case, we had 2 machines, 2 types of products, nothing else but just machine hours. Fine. That was milk production. We're done with it. Blending. Let's read what the problem says. Now we're looking at an oil refinery. Okay. We're distilling crude oil. The crude oil can come from Saudi Arabia or Venezuela. Okay. So we have 2 different types of inputs. All right. But we're a refinery, yeah? So we're going to change them. We're going to refine those crude oil and form gasoline, jet fuel, or lubricant. Now, for each ton of Saudi Arabia oil, we're getting 0.3 of gasoline, 0.4 of jet fuel, and 0.2 of lubricant. Fine. So this is the yields of each Saudi Arabia crude oil. If I'm using Venezuela oil, the percentages are different. This time I'm getting more gasoline, less jet fuel, a lot of lubricants. Okay. In each type, I'm losing 0.1 tons for refining operations. Okay? Clear up until now. I have 2 types of oil. I'm putting them in, both of them goes into refinery, and both of them gives me different proportions of jet fuel, gasoline, or lubricant. Okay? Do you think we are ready? No, yeah? You don't know anything yet. We just know that there are 2 types of oil that I can use. Okay, what else? Coming in. Saudi Arabia oil costs $600 for each ton, and Venezuela oil costs $550 per ton. A little cheaper. The availability, I can only buy 60 tons of Venezuela and at most 90 tons of Saudi Arabia. Okay. And well, why am I doing this? Of course, the crude oil doesn't go in the market. I have to refine it. And my market is asking me gasoline, jet fuel, lubricant, right? So I'm supposed to come up with 20 tons of gasoline, 15 tons of jet fuel, and 5 tons of lubricants every day. And every other thing is daily, all right? So, how should the demand be met with minimum total cost? I think we're ready now, yeah? We have all the things that we require. Clear? Let's think about the decision variable. Yeah. What do you think is a correct decision variable? Think. Yeah. So we have how many decision variables? 2. The suggestion is we have 2 decision variables. We're going to represent one of them for Saudi Arabia and the other one for Venezuela. All right, now let's do this. And I hope it works. Okay. Comment. Yep. So, I buy it, so X1, no, come on, change the color. X1 will be number of tons of Saudi Arabia distilled daily, oil, distilled daily, and X2 will represent number of tons of Venezuela oil distilled daily. Yeah? Clear? Yes, I did it. Okay, what else? Now we have defined our variables. Let me bring back, if I go back, will it come back? Yes, okay. So I'm here then. Tell me the performance measure. What is the performance measure? Come on, what is the performance? Someone else, yeah. Minimum cost. Now remember these numbers so that you're gonna tell me the cost function, right? I'm there, so we're gonna minimize what? Minimize what? Yes? Very good. Subject to. Let's go back. What do we need? We need to satisfy the demand. Yeah? I can't hear you.
We can categorize the total number of purchased from Saudi and Venezuela, and we can say that, like, we can set the constraints as 90 tons at max from Saudi and
That is true. So you want to write, okay, say it in mathematics.
X1 is less than or equal to 90.
Hold on. X1 less than or equal to? 90. Yep. And X2? Correct. How about this 20, 15, and 5? Right? Now, if I don't say anything else and just leave this like this, optimum solution is 0. Right? Don't produce anything. Cost is 0. Right? So we have to tell the model that there's some, I have to make sure that I have 20 gasoline, remember? I need to have 20 tons of gasoline, 15 tons of jet fuel, and 5 tons of lubricant, right? Now I'm bringing you this slide. Try to remember, so let's memorize the gasoline. 0.3 from Saudi Arabia and 0.4 from Venezuela. Now let's write the constraint for gasoline then. So the constraint for gasoline is 0.3 times Saudi Arabia plus 0.4 times Venezuela is at least 20, no? Yes? Okay. The others were, I have it here so I can cheat, 0.4 x1 plus 0.2 x2 should be at least 15. Yeah, I have to learn how to write here. I'll continue like this, but it's in the same, all right? 0.2 x1 plus 0.3 x2 should be at least 5. So now x1 0, x2 0 is no longer feasible, right? Because I have to have 20, 15, and 5 with certain multiplications. Great? Anything else? Or is it done? Exactly. Because for the model, if I give it like this, it may say, okay, x1 is minus 20. But that doesn't mean anything in real life. So I again have to tell that I'm in first quadrant. So I have to say that x1 non-negative and x2 non-negative. Now we're done. Done. This is the model. Yeah? Any questions? Clear? Okay. I don't like you taking the pictures of this. At least write it, all right? Next time. You may not be with a piece of paper this time, but for Thursday, whatever your notebook is going to be, come here with that. Yep. Yes? No. Write them on your own. It's just one slide this time. It will be 4 slides on Thursday. Only the models will be empty in the PDF, but I want you to write on it. That's why maybe you may decide to print them out, use it as your notes, because we will always write. Hold on. I didn't say we're done. Hello. I didn't say we're done. Thank you. I'm hungry too, don't worry. We're gonna go. Make sure that you did this because your first quiz will be asked from Piazza about the things I talked about today, all right? And we will be meeting Thursday at 8:40. Do not come to class late, okay? Today I've seen a lot of people coming late. This was the first hour. From now on, I'm not gonna let that. Okay, now we can go. See you on Thursday morning.